Okay, we're going to start the lesson on polygons and congruency. Congruency is basically a fancy word for a copy. It's exact same size, exact same everything. But first we're going to do some polygon information. And we're going to start with the fact that the interior angles, the inside angles of a polygon, can be found by the sum, we're going to add them, of all the interior angles. And we have this nifty little formula of 180 times n minus 2, where n equals the number of sides of the polygon. If we look at a polygon, and let's say I've forgotten the formula, I can divide this polygon into triangles and multiply the number of triangles to get the number of sides. And when you look at this formula of 180 times, in this case my pentagon, 5 minus 2, I end up with that 180 times 3. So just remember, you can always, when in doubt, divide it up into triangles. Now that's the sum of all of them. So for example, what is the sum of the interior angles of a hexagon? Well, a hexagon has 6 sides. So I have 180 times 6 minus 2, which is 180 times 4, which is 720 degrees. Now I don't know how that 720 degrees is divvied up amongst the angles. I just know that that's what they add up to. So in our old problems, we would set triangles equal to 180. We would set quadrilaterals equal to 360. Now we have new sums that can be used. Now, what is the number of sides in a polygon if its interior angles have a sum? Here I'm going to give you the sum. So I'm going to set up the formula. 180 times n minus 2 is equal to 2,520. And now we need to solve for n. Quickest way here is to divide by 180. When I take 2,520 divided by 180, excuse me, I end up with n minus 2 is equal to 14. When I add 2 to both sides, I get n equals 16. So a 16-sided figure has a sum of 2,520. Now, what is the measure of one interior angle in a regular pentagon? Now, regular is a key vocabulary word, and regular means all the sides and all the angles are the same. So I can take the sum of all of the interior angles, and if I divide it by the number of sides, that will give me one interior angle. But that only works for regular polygons when everything is divvied up the same. All the sides are the same, all the angles are the same. So a pentagon would be 180 times 5 minus 2 all over 5. So I have 540 divided by 5, which is 108 degrees. Every angle in a regular pentagon is 108 degrees, excuse me. Now, exterior angles of a polygon kind of feels like a trick question because no matter what kind of polygon we have, the sum of all of them is 360 degrees. Now, what does the exterior angle look like? If I take my shape drawer again and I draw a shape like this, the exterior angles, if I start on one side and I extend going in the same direction from all the sides, these are my exterior angles, and they are the ones that add up to 360 degrees. So if I look at the sum of the exterior angles of an octagon, doesn't matter how many sides, all of them are always going to add up to 360 degrees. If my octagon is regular, that means they are all the same, and so I take 360 and I divide it by 8 to find out that they equal 45 degrees, each of them. Now, congruent polygons have all the same shapes, all the same side lengths, all the same angles are the same. But key word in this is corresponding. They have to be able to match up. Like I described it, it's an exact copy. A congruence statement is a very important idea. And this is where I'm going to say, for example, triangle this is congruent to triangle that. And every vertice of that triangle has to match up. So for example, when I look at these quadrilaterals right here, if I say quadrilateral MNO, LMNO, okay, I can name them in any order I want, go clockwise, go counterclockwise, just don't hop and skip across, is congruent to. Now L looks like it corresponds to W. Now I went to M, is going to correspond to Z, N corresponds with Y, and O matches up with X. That is a congruency statement. So for these congruent triangles, if I say triangle BCA, start here and go this direction, the one that appears to line up with B is E. And if I continue in that same direction to the shorter side, I have EFD. These are just congruent by their shapes. There's no vertices. And this one is just to show you that these are not congruent, even though they are what's called similar. And we will talk about similarity in a later chapter. Congruent means an exact copy. So for some examples, quick example, some sort of a quadrilateral with opposite angles equal. Can't be a triangle. This one has similar angle measures, but they're not in the right order, so they would not match up. C is the one that, while it is twisted, would match up exactly. Now this example is an important example because it teaches you about the importance of this congruency statement right here. That is your directions. When I look at the pictures, it's kind of hard to tell what's going to match up with what. But if I want to know what side is congruent to CD, I don't have to worry about the picture and trying to figure it out. If I go to CD in my congruence statement and I go to their corresponding positions, I find out that CD is congruent to IJ just from the congruency statement. So if I asked you what is congruent to angle E is second to last. That is congruent to angle K. If I asked you what is congruent to side LG, that goes last to first, last to first. That would be congruent to FA. And if we mark our picture, you can begin to see that these indeed, with a little bit of a twist, would match up. Now, corresponding parts of congruent triangles are congruent is a very, very important and useful theorem that we are going to use in 3.2, 3.3, and 3.4. The key here is that you must know congruent triangles first. If you know congruent triangles, and congruent triangles are going to take 3 pieces to prove congruency, you're going to get all other parts congruent. I call it a buy 3, get 3 free. So in this triangle, again to practice congruence statements, I have triangle ABC is congruent to triangle A has a single hash that corresponds with D, B is a double hash that corresponds with F, and E and C match up. All 6 parts are marked here, and when we start talking about the different ways to prove congruency, you'll see how CP/CTC will come into play. The isosceles triangle theorem is something we've talked about before, In the converse, we are going to lump together and we are going to call the Isosceles triangle theorem in all of our proofs. And basically, if you know equal sides, you're going to get equal base angles. Or if you know equal base angles, you get equal sides. A very powerful theorem. Remember that the base angles are the ones that are opposite the right angle, or opposite the equal sides, and vice versa. That is a super powerful theorem as we move to congruent triangles. A couple of examples. These are using the isosceles triangle theorem. So obviously if these base angles are equal, that means that these sides are equal. So 15 is equal to 4x plus 3. Subtract 3 from both sides. Divide by 4. And 3 is x. This is a two-step problem in number 2. Here are my equal sides. So that means that these base angles are also equal. So I have to start there. 3x minus 11 is equal to 2x plus 11. So for x is 22. But I'm not done. In order to find out y, I have to take my 22 and put it into these base angles, which end up being 55. And then to find y, I have 2y plus 55 plus 55 equals 180 by the triangle sum. So I have 2y plus 110 equals 180. 2y equals 70. Y